They took away my first slide, so that's interesting. But it said that I'm part of the Ohio State University Physics Education Research Group. And so you need to know a little bit about physicists and how we're distinct from mathematicians and engineers. So here's the thing. You set up an experiment. You go into a room, and in the room, there is a curtain blowing over a window, and there's a pot of water on the table. And so the experiment is this. Someone sets fire to the curtain in the room, and then the mathematician walks in. So mathematician looks, hey, there's a solution, turns around, leaves the room. The engineer walks in, and the engineer sees the burning curtain, the water, gets over, takes the water, runs it along a very straight line along the curtain, and leaves the room. The physicist comes in, sees the burning curtain, sees the water, picks the water up, throws it on the curtain, and there it is. So we physicists are practical, but maybe we leave a few tatters hanging sometimes. Let's see. Ooh, I turned it off. Which way does it go? This way. All right, so what I'm going to talk about is a bridge to the future. And nuclear energy, I think, is a bridge over the 1 or 2 centuries that we're going to need. Now, why do I say 1 or 2 centuries? I want you to look at that number. That number, that's the power that the sun sends to Earth. It's a big number. There's the sun. We receive just a tiny amount of its power, but that tiny amount of its power you just saw there is very large. This number is the total power that we as humans use here on Earth. Electricity makes up about 6 terawatts, total is 16. Obviously, there are other things in there. So I want you to look at that ratio. The total power received from the sun, the total power used by human beings, and look at that ratio, about 7,600. Now it's true, we don't get 100% conversion efficiency, so even if we take a factor of a third, that's still 2,500 times the power currently used by the human race. The future, folks, is solar. It is. We have no choice. The future is solar because there is that much energy coming to Earth. We need that energy. We can use it. But we got to get there. Look at our current use. This thing I got from the annual energy review that came out last Friday. And it's the U.S. energy flow last year, 2011. Now, I'd like you to look at this, and there are only 2 little things right here, this one there and the one right above it, that are not fossil fuel. Fossil fuel is stored solar energy, and we are using it like gangbusters. You can see where it's going: transportation, residential, commercial, and so forth. This is another view of it. So U.S. energy sources, again, you can see the first 3 are not renewable, they're not nuclear, they are fossil fuels. That's what we use right now. This is a picture of the last 10,000 years of emissions of greenhouse gases from the Intergovernmental Panel on Climate Change last report. So the first one that you can see in the upper left is carbon dioxide. And you can notice about 7,000 years ago or so, it started rising gradually. And then all of a sudden, there's this huge bump. What the heck is that? It's the Industrial Revolution. Look at the change. The second one down there is methane, a very powerful greenhouse gas, molecule for molecule, probably 25 times as effective as carbon dioxide at heating atmosphere. And the third one is nitrous oxide. Again, you see the effect of the Industrial Revolution. We're not playing around anymore. We are changing the world. This is a picture of Europe over the last 2,500 years. The rainfall and the temperature is gleaned from tree rings. Bunken et al. Last year in Science magazine. Now what I want you to look at is over on the far right. You see that thing going way up? That's us. Now, compared to everything else. You may have heard people talk about the medieval warm period, the Roman period. Look at how much higher Earth's temperature is now than it was then. So what are we talking about when we're talking about fossil fuels? Well, there are three major ones: coal, oil, and natural gas. Then they're really concentrated energy, stored solar energy, about 25 megajoules per kilogram for coal and about 83 megajoules per kilogram for natural gas. Now, a kilogram of coal has about 93% or 94% carbon. It means that there's a lot of carbon emitted when I burn the coal. And you can see here that there's about 4 times as much carbon emitted when I burn coal as when I burn natural gas. Over a 50-year lifetime, the 1,000 megawatt plant is 1 gigawatt plant. That's a typical power station nowadays. Coal will release, over a 50-year lifetime for that plant, 655 megatons of carbon dioxide to the atmosphere. Oil, about half that. Natural gas, about a quarter of that. This is a history of carbon emissions, carbon dioxide emissions, actually, since 1750. What I want you to concentrate on is, say, 1880 or so, when it starts getting a little above where it was before, to the present. Look at that thing go. Shoo! Up like that. It's amazing, isn't it? And take a look at what happened. This is the world, and what I've done is to take the 25 coldest and 25 warmest months. And so we have 130 years worth of stuff. There are a lot of them. I've plotted them on here. Take a look at where all the coldest months were. Take a look at where all of the warmest months were. Go back and look at this. We see there's a correlation. Now, what's going to be a consequence of a warming world? This happened in 2003 in Europe. The blue line is the mean mortality in Europe during this month. So day by day, averaged over those years, those 3 years. And the red line is what happened in August of 2003, the European heat wave. Look at how many people died. It is predicted that with global warming, we will have many more such heat waves in the future. This is a report of the US government on global climate change, or in the world here, and it focused on the US. And you'll notice from this picture that most species seem to be moving north. Over the period listed here, it's moved something like 30 kilometers north. And I just had to show this. My wife told me, you're not supposed to put these things up there. You can't talk to an audience like this and show them the titles of articles in scientific journals. But I couldn't help this. Look at this. Are lizards toast? I just couldn't help it. It's about this article, Erosion of Lizard Diversity by Climate Change and Altered Thermal Niches. What they did a study of Mexican lizards. Since 1975, 12% of Mexican lizard species have gone extinct, and more are going to go extinct. Why? Because of the way things happen. They used to go out and bask, they would eat a little bit, they would have time for meeting the opposite sex, and there'd be more lizards. Well, now it's gotten hotter in the Mexican deserts. They don't have as much time to bask, they hardly have time to eat, and guess what they don't have time for? And so lizards are going extinct. This is another picture from that same report on climate change in the United States, and this is a prediction for 2050. Now, I wanted to have an Ohio state thing. You know, I'm part of Ohio State. So, but they showed us Michigan, sorry, the state up north. Anyway, what you can see here, the sort of yellowish one is the lower emission scenario. That means we actually do something to try to reduce fossil fuels. The red one is the high emission scenario. We haven't done very much to lower fossil fuel use at all. And you can see Michigan, if we have the high emission scenario, ends up being like the Texas Panhandle. We're even lower than them. Think about that. What's Ohio going to be like in 2050 if we can continue to emit stuff from fossil fuels. This is this year, March 2012, and the red dots showed where the daily record highs were broken or tied throughout the month of March. You may even remember, March here in central Ohio, those of you who live here, was pretty darn warm. But it's not just this year. This is last year. Look at all those red dots. They're the same thing. The blue ones are the cold records, and the red ones are the hot records. 6 months worth of last year. Now, what are the other kinds of things that are happening there? You can see, for example, that little line that goes up there, that's the median from 1979 to 2000 of the Arctic ice cover. The white is the Arctic ice cover in the middle of last month, September 16th of 2012. Look at that. Look at that. And the chart up here on the upper right shows from 1979 to the present, and you can see that the ice cover has been going down. There was a big drop in 2007. It recovered a little bit. The big drop here in 2012. And down below is over a little longer time period from 1900 to the present. You can see up until about 1960, it was pretty much constant, and then we started a pretty precipitous decline, going down and down and down. So we cannot afford, as the human race, to continue to do this to our planet. And so we need to get to a future where we can use that solar energy. To get there, we need a bridge. And I think that bridge is nuclear energy for several reasons. They don't produce any greenhouse gases. They can, I know you don't believe this probably, but they can be built in a reasonable time frame. If we have uniform design of the 104 reactors in the United States, almost all of them are one-off. If we didn't do that, it would be better. And you might or might not know this fact, but if the Nuclear Regulatory Commission were to regulate coal-fired power plants the same way they regulate nuclear power plants, every coal-fired power plant in the country would be shut down because of the release of radiation up the stack. This is a picture of nuclear electricity worldwide as of the middle of this year, and you can see the United States does have the largest number of reactors, followed by France, Japan, Russia, Korea, and so forth. Now, the problem is almost all of those reactors you saw in that chart up there are old technology. What do I mean by old technology? I mean 1960s technology. Would you drive a 1960s car? Probably not. Do you watch a 1960s television? Probably not. 1960s technology was great for the 1960s. We live in the 21st century, 50 years on. Most of those reactors are the things up there, Generation 2. But nowadays we have Generation 3 and Generation 3 Plus. They are much improved in many aspects, as we'll see on the next slide. The last of these is called Generation 4. Nothing in Generation 4 is operational. That's where the research is going on. But those reactors, it says it's safe. Well, in the first chapter of my book, I point out TANSTAAFL. Now, T-A-N-S-T-A-A-F-L means there ain't no such thing as a free lunch. Nothing is going to be safe. Nothing is going to be safe. I could walk off this stage, kill myself. It's easy. In fact, I've done it giving talks other places, fallen off the stage. So it's possible to do that. Now, I talked a little bit about efficiency when I talked about the solar energy, that factor of a third. Really what happens in general is if we have a source of energy, we have to convert it. A lot of times those processes are thermal processes and involve thermodynamic efficiencies. A typical efficiency of a current power plant operating in the United States, coal-fired, is about 30%, 33 actually. Same for a nuclear power plant. What goes on, that means that 2/3 of the energy we're burning goes to waste. Only 1/3 of it goes into electricity. What a waste. We shouldn't do that. But we have to because that's the way it is. We have to, by the laws of thermodynamics, put waste energy into the low temperature reservoir, and all of you know that has some effects, for example, in Lake Erie and other places. But out of that, we get wonderful things like all the electricity used in this room, useful energy, mechanical, electrical, and thermal too. So I'd like you to look at this chart. This I stole from CPEP, the Contemporary Physics Education Project, of which I'm a member. This is from one of our charts. And what it shows is a comparison of chemical, fission, and fusion reactions. So what you've got to see here is that the energy released per unit of fuel, as I said, roughly for fossil fuels, something like 30 megajoules. That's what that 3.3 times 10 to the 7 says, right? The fission reactor gives you about 100,000 times as much energy per kilogram as we get from a coal-fired plant. And if we have fusion, still if we have fusion, it's 10 million times. So what are the advantages of these Gen 3 and Gen 3 plus reactors I've talked about? Well, first of all, there is reduced piping. So part of the problem, the complexity of these nuclear plants, there are water pipes all over the place, valves all over the place, and it's really, really difficult. If you reduce the complexity, you reduce the chance that a human is going to make a mistake. And that's one of the other things that we have to worry about. 3 Mile Island was caused by humans. Chernobyl was caused by humans, particularly stupid ones, I have to say. Anyway, but the other thing that the Gen 3s have are passive safety. That is, they don't rely on outside power. If Fukushima had had passive safety, there wouldn't have been a problem. And finally, the NRC is licensing designs that reduces by years, because they do it all at once, reduces by years the licensing. Now, there are drawbacks. And I would be crazy if I didn't tell you that there are drawbacks. Remember Tanstaffel. But here's a list of things that I've garnered looking at the sites of people who are activists, anti-nuclear activists. And I have about 2 minutes left, a minute left. I'm obviously not going to be able to address all of those. But plants cannot blow up. Nuclear, weapons-grade uranium's 90%. These plants are 4% uranium. No way can they blow up nuclear. Now, they can have hydrogen explosions, which is what happened at Fukushima, as you may be aware, and also happened at 3 Mile Island, but not nuclear. They say nuclear power is unaffordable. Well, look at what we get from conventional power. 25,000 people in the United States die prematurely every year because of coal-fired power plants. 250,000 people suffer from COPD, asthma, emphysema, and other things because of that. And not only that, there's this thing I took from my energy book where I did a study and looked over costs per capita of pollution in various places. These were the ones I could find. And you can see they range from about $250 to almost $1,000 a year for people in various parts of the country. You and I pay these costs because we're emitting stuff from coal-fired plants. What about the nuclear waste? Well, in one sense, you may not believe this, but nuclear reactors actually clean Earth because we're making the radioactive decay happen a whole lot faster in the nuclear reactor than it would happen in Earth. Of course, we've concentrated it, and that means that we have waste that we have to get rid of. But if we could make that waste decay faster, that would be even better. Now, what kinds of solutions are there for waste? Believe it or not, there really are some solutions, not all science fiction. One of them is simply to have what's called a breeder reactor. Now, there was a lot of research done in breeder reactors in the earlier years in the United States. They shut down the last breeder in 1970-something, 75 or 76. But breeders actually can breed fuel, make more fuel. The typical reactors we have now are called burners, okay? But there are breeders. They make fuel in addition to burning the fuel, so they can produce electrical energy and make fuel that can be used in conventional reactors. In the case I have up here, a thorium breeder could produce uranium-233 that could be used in, let's say, Davis-Besse or Perry here in Ohio. This is a concept, certainly has not yet been proved because they haven't had the NIF work, as I'm sure you're aware, it missed a deadline. But anyway, here's a concept called LIFE. It's a fission fusion chamber. So what you do is you put a little seed of stuff in the middle that we're going to fuse using lasers, and around it you put a whole bunch of other things. And those things get burned up. It is thought that they would produce, by the end of burning, if you used life, all of the reactor stuff from the United States and all of the weapons stuff from the United States would end up being 40 megatons of waste to dispose of. We need a bridge to the future. I think that bridge to the solar future is nuclear energy. And thank you very much.